Might just be because I'm so strong. So, okay, so like I said, what we're going to talk about today is integrating through vector fields. Okay, and so remember kind of what we define a vector field as is for every point in space, we define a vector. A function assigns that point a vector. And we can think about it in two-dimensional space or three-dimensional space, kind of in five dimensions. Mostly we think in two-dimensional space. So that's kind of how we are. So let's kind of think of like a good physical interpretation of this, like a good reason for why we want to do this. So what can you think of like something that would go along the path through a vector field that we might want to think about? First of all, what does integration do? Like kind of what is integrating do? It's an infinite sum. So we're kind of adding things up. Okay, so think of like when might we want to add up a bunch of values in a vector field? What do vector fields often represent? Yeah, yeah, so we can kind of think of them as like, a lot of times they apply to like topography or when we think of map making. But remember also we thought of vectors as being like a force field. A vector field we can kind of think of as representing a force field, like gravity or electromagnetic field or something like that. So it won't quite be the total force because we're doing line integrals, and so kind of what the physical interpretation is going to be is. Remember, way back in the day, we looked at first how a vector in one direction does work along a vector in another direction, and so now we're going to kind of extend that and think about like a vector field doing work on a particle as it goes along the path, and then what we can do is use the integral to kind of figure out the total work, and so that's kind of what if we have this particle moving along a path C. Through some vector field, and we can just kind of be general about the vector field for right now, then we can use a line integral to figure out what the kind of the total work done by that vector field is going to be on that particle. Okay, so let's kind of look at what that's going to look like. Okay, so I'm going to make this bigger. So, yeah, definitely. Well, I'm going to make those a lot shorter. They're not going to be as long, so I'm not going to kind of ramble so much. Okay, so kind of what we have to imagine is we have a path C that's going through space. Okay, so it's just kind of winding through space, maybe going like this. I don't really know. Okay, and remember, a vector field assigns to every single point. It assigns kind of a specific vector, and so what that would look like is that if we have a point here on our curve, then that's going to have a specific vector assigned to it. Okay, and remember they can kind of go however they want. Well, that's actually, yeah, so that's going to be the way the particle is moving. Okay, so in other words, we kind of like pick some point here on our curve that's like x, y, and z. And so x, y, and z lies on the curve x, y, and z, not x, y, y. X, y, c is on our curve C. And so this blue vector right here would be f of x, y, c. X, y, c. What am I trying to say? Okay? And so it's just kind of some vector. It just assigns at some point, some direction, and some magnitude. And then, but you were kind of going in the right path, thinking in the right direction, thinking about the same thing. Because we remember way back in the day when we want to figure out how much some given vector is doing work in another direction. Does anyone remember how to do that? Yeah, it's the dot product. Okay, so in other words, we're going to kind of think of taking the tangent vector here. Kind of cramped up. This is our tangent vector. And that's the direction of the particle. Okay? And so what that means is the work done by our force F at our point x, y, z. We can approximate that work by taking the dot product of that force vector and the tangent. Okay, so that's kind of what it all comes down to. And then we can think of, well, going back to our integrating infinite sums, we can, if we break each of these into little pieces and get a sample point from each one, take the limit and sum them up, it'll end up kind of taking into the integral. Okay? And so, this is what it kind of looks like when we put it into the integral. So we're going to get this length element here, because we're breaking it into little delta s's. But we're just going to have the dot product of the force vector and that tangent vector. And so when we kind of take the limit and sum them all up, we're going to get what we call this like line integral through a force field. So notice all it is the dot product of the force field and the tangent vector. And so this is the tangent vector for C. Yeah, so that's like the tangent along that curve. C, where we just have some parameterization. Okay? Oh, thanks for the heads up. Okay. Yeah, and so we kind of have a convenient way that we can rewrite this to make it look a little more useful. Again, if we think of R of T as being a parameterization for C, okay, so then, like I have written right here, I'm going to write a little bigger. T of T equals R prime of T over the magnitude of R prime of T. And we actually, again, kind of thinking back just a little bit to last week, we saw that ds, which was that kind of, remember S is arc length, so we can think of the change in arc length as being dx dt squared plus dy dt squared plus dz dt squared. But what this really is equal to is just the magnitude of the tangent. And so then ds equals the magnitude of the tangent vector times dt. So that was kind of that change of variable that we use to carry out this integral. Okay, and so if we kind of substitute this all back in, we're going to have the integral over c of f of x, y, z dotted with r t, r prime of t over the magnitude of r prime of t times the magnitude of r prime of t
going to be recorded forever. There we go. R prime of T. T. So notice that these cancel out. And we come down to this nice kind of concise formula. And so a lot of times this is kind of also abbreviated a little more shortly. Remember how we up here we call dx the magnitude of r prime of t dt. Well, we can call r prime of t dt. We kind of call this little notion, this little thing right here, just dr. And so the other way it's often written is the integral over c of f dotted with dr. So it's a little kind of funny to think of having the dot product of our differential in the dot product or in the integral, but this is really all it means. It's just dot product of the vector field and the tangent vector. Okay, so this is kind of, all the different ways we have to write it. We have f dot with dr. Here again, we kind of think of RT as being a vector, so this is a vector function on a vector, dotted with the derivative or the f, or f dotted with c dotted. Okay, so that's how we define a line integral through a vector field. So let's kind of look at a couple of, I don't know. Oh yeah, I already said that. So okay, so let's kind of look at a couple of examples of how we carry out these computations, because they're really pretty straightforward. Okay, so this is just a two-dimensional vector field. You can see x and y, and we just have these two components, I and j. So it's going from 2 dimensions into 2 dimensions. And notice it already gives us the parameterization. Okay, so we're integrating the quarter circle here just from 0 to pi. Okay, so when we set up this integral, we want to find the full work done. So it's going to be an integral over c of f of xy dotted with r prime and so when we switch coordinates, what is f of xy going to kind of look like? When we want to switch integrating just with respect to our parameters. What is f of xy going to look like if we switch to our parameters? So yeah, so x equals cosine of t and y equals sine of t. And so f is going to kind of turn into this vector cosine squared t, and then negative cosine t sine t. And we're taking the dot product with r prime of t. So rt is cosine and sine. R prime of t is going to be negative sine of t, and then cosine of t. Okay, and we're going to just be integrating from 0 to pi over 2. And we can kind of put this balance now that we switched everything to the end term. And luckily, I think this interval is actually going to kind of work out to be relatively straightforward. Because we're going to have cosine squared t times negative sine of t. So negative cosine squared t sine of t. And then we have plus, because it's the dot product, but we have this minus here. So we're going to have minus cosine squared t sine of t. dt. Okay. What are any ideas about how to carry out that integral? Yeah, we can just do substitution pretty straightforward. Okay, so what is u going to be? U is going to be cosine of t. So du is going to be negative sine of t. And so I think that we're just going to have 2u squared. 2u squared du. And so that's going to integrate to what, 2/3 u cubed? And can I go ahead and switch back to cosine? Because that's what u was. I'm going to evaluate from 0 to pi over 2. I think cosine of pi over 2 is 0. So it's going to be 0 cubed minus 1 cubed. So I think it's going to work out to be just negative 2/3. This is minus.
Okay. On the left, what is it?
Yeah. Okay, so are there any questions about that one? Okay. Down. Yeah. Pretty nice. Yeah. No, so kind of what this is like this is just like kind of the sum of all the work. So this is kind of an independent a unit list. I guess what is work is normally in joules. So, this just has to do with like so in other words this vector field F is like a force field. Maybe it's like a magnetic field or something. And this particle is moving along this quarter circle from here. And if we kind of went through and looked at the vector field, it's x squared, so it's as it goes to the left, they're getting stronger and stronger pointing that way. And so it kind of makes this funny shape, but in general they're pointing to the right, and that's why it ends up being negative, because this particle is going to the left. And so like these vectors, most of these vectors are kind of pointing that way, and so it's kind of negative work. And so all it is kind of the total amount of energy used by that vector field on the particle. Yeah. Okay. So let's kind of look at one more example in, in 3 space. Just notice here, now we have a function of 3 variables, x, y, and z, and the vector that's getting spit out has 3 components, an I, j, and a k component. Okay, so we want to, RT here is the twisted cubic, so it's t squared, and t cubed. And so R prime of t is going to be 1, 2t, 3t squared. And if we want to kind of think of putting f in terms of t, the first component, the ith component, is going to be x times y, which is t times t squared. We're going to have t cubed. And then the jth component is going to be y times z, which is t squared times t cubed. That means t to the 5th. And then the last component, the kth component, is going to be x times z, which is t times t cubed. So this is going to be it. Okay, and so our integral is going to kind of look like, remember, we're going to have f dotted with r prime of t dt. And so if we go and switch our bounds, or switch our kind of integrating this with respect to t, when we take this dot product, well, I'm just going to write that first. Which was t cubed, t to the 5th, t to the 4th, dotted with 1, 2t, 3t squared. See? I think we'll have t to the cube, t cubed, plus 2t to the 6th, plus 3t to the 6th. And so, when we integrate, this is going to turn in t to the 4th over 4, and then this is going to be 5t to the 6th, which will integrate to 5t to the 7th over 7. Graduated from 0 to 1. So I think it's just going to be 1/4 plus 5/7. Which is going to be 27, 28. That's going to be 7. And that's going to be 20. 27 over 28. And so notice the last one was negative, which meant that that vector field was doing negative work, and this one is positive, which means it was doing positive work. Okay, so kind of this vector field was moving this particle. We can kind of think of it as going, helping this particle along, whereas when it's negative, that means it's kind of going against the particle. That means the particle is going in the opposite direction of the vector field. Okay, so let's kind of take a look at this, because this is going to kind of come full circle and connect back with something we looked at yesterday, or not yesterday, because none of us were here yesterday. Oh, on Friday. Were you? Yesterday, yeah. This month. Right. Yeah. So we can kind of think of rewriting this as this vector EQR. And again, these are kind of all functions of x of t, y of t, and z of t. So we can expand it out a little more. But let's just kind of take a look at this. And remember, this is going to be dotted with r prime of t dt. Okay, and so when we expand this out a little more, y, t, dt, t, comma, q of x of t, y of t, z of t, comma, r, x of t, y, and that's going to be dotted with, well, if we want to expand r of t out, r prime of t rather, because r of t is x of t, y of t, z of t. So r prime is just going to be the vector x prime of t, y prime of t, z prime of t. dt. Okay, so kind of take that in for just a second. It looks pretty nasty. But when we evaluate this dot product, notice we're going to have t times x prime of t times x prime of t plus q times y prime of t, and then we get r of t y to t times z prime of t. So that's just the dot product, and then all times dt. So that dt is still getting distributed over everything here. Okay, still looks kind of nasty, but notice that when we distribute, and I'm going to simplify this really quick by just writing x, y, and z. We're going to have x prime of t times dt. Here we're going to have plus q of x, y, and z times y prime of t dt. D prime of t dt. But what is x prime of t dt equal to? We have a really simple way of writing that. That's just dx. And this right here is just dy. And this is just dz. And so what it kind of cooks down to is just the function t integrated against x plus the function q integrated against dy, and then plus the function r integrated against dz. That's integrating we have a vector field that's like PQR, and we have RP that we're integrating it over. Then it just kind of turns into this. It's a much neater and easier formula. And so we kind of looked at this already yesterday, or on Friday and on Thursday, kind of integrating these line integrals we have with respect to different variables. And so that's kind of integrating over a vector field. Just turns into integrating kind of the x component with respect to x, and the y component with respect to y, and the z component with respect to z. And so that's why those, remember I said how the integrals with respect to those different variables would come back and make a little more sense. Now what we can think about is, well, this vector field is doing this much work in the x direction. So if we want to kind of add its work, all we're going to be concerned about is integrating that in the x direction. And then, you know, the j component is in the y direction, so it's doing q amount of work in the y direction. So we integrate q with respect to y, the same way with r and z. So it's kind of intuitive, you know. So that's all there is with line integrals. And so I think that's where we'll stop for today. I have some practice problems for you all to work on, but I'm actually gonna like go through and watch this video. Yeah. Let's kind of watch this and let me know what you think. But are there any questions before we do that on this kind of stuff? It's pretty straightforward. And I think as we get through the rest of this chapter, even though it's going to get a little more technical, a little more abstract, it actually will kind of end up tying all these things together. The next few days are a couple of theorems that I think this will help tie everything together. So, okay, let me.